the Kelvin scale, named by Lord Kelvin, an astronomer scientist which was born in 1860, is really good. However, if we related it to room temperature, which is about 21 degrees Celsius or 70 degrees Fahrenheit, it will be about 294 Kelvin. The lower temperatures, the lower limit is about absolute zero or 0K. No, OK, which means 0K. What I'm trying to say is 0 with the absolute 0. So what is absolute 0? Well, what we feel in this temperature is atoms zooming around and bumping into each other. Like us, when the motion stops, we reach absolute 0. Except you can't actually reach absolute 0. Although absolute 0 is really hard to get, and because of a reason that I'll tell you in the end of the video, you might think that absolute 0 cannot be get. However, scientists are trying to see how low we can get. For example, in 1847, this guy liquefied helium to 1.5 Kelvin. And in the 1900s, scientists used lasers to squeeze atoms, reaching a low temperature of 360 millionths of a Kelvin. That's almost rarely above absolute 0. Crazy, right? But at these temperatures targeting at absolute 0, physics becomes a little tricky. And that's why scientists also try to use really hot temperatures to see how hot we can get. For example, scientists at CERN used racetracks with magnets almost 16.6 miles long. These help the gold and lead particles to accelerate at nearly the speed of light. They flash, bang, and smash into each other, creating an environment that was similar to the 1 millionth of a second after the Big Bang. So hot that the only things that were existing were quarks, gluons, and electrons before they cooled enough to form the atoms we see and love today. They heated up to temperature to more than 5 trillion Kelvin. That is extremely hot. And that makes me sweat. Just kidding. However, that means what is the hottest temperature possible in the universe? Well, the answer to that is the Planck temperature, or 142 million degrees Celsius. We don't know what actually will happen if it is as hot as the Planck temperature, but we do know two things. One, for this temperature to actually come into existence, everything has to come in thermal equilibrium. And two, remember that if we heat something more than 142 million degrees Celsius, the object will be hot enough that it will actually turn into a black hole. That's not good, because if you have a black hole, it will suck everything and destroy the whole universe in just 100,000 years. That isn't so long. It might be really young in years, but it's just over 100 millenniums, which is not good.
Done?
Yeah, I mean, if a black hole absorbs the whole universe in just a few days, just a few hundred 200,000 years, that means we'll be totally dead in just one day. No, not even one day, in a fraction of a second. Because the universe is tons and tons of times bigger to it. In fact, the Earth within the observable universe is equivalent to a virus hanging within the solar system. But that doesn't make sense, because we not only can't appreciate how small a virus is, we also can't appreciate how big the solar system is either. In fact, a virus is just about 700. In fact, the average virus is only about 700 to 400 picometers in size. Just over 400 times. That's just over 4, which is just 4 times bigger than the uranium atom. That's really tiny. But our solar system, on the other hand, is a massive one. Is more than 3 light years wide. However, our actual solar system is almost 2,000 light years wide. That's as much as the thickness of the Milky Way. Quite crazy, right? But this means that the Milky Way is about 50 times wider than it is thick, which makes quite nice sense. But even though these temperatures are really hot, when there's something that happens which is really cool at the tiniest temperatures. When we think that atoms just won't stop. However, when it gets super cold, like 100 billionths of a Kelvin or 100 nanokelvin, the atoms start acting in their own way and together. And the colder it gets, the slower and slower the atoms get. However, there is a problem, because we can't know how fast enough is going to know where it is. Because even when it collides with something, it will slow the thing down, but we won't know how fast it was going, just where it is. However, if we knew how fast it was going, about 300,000 kilometers per second, we wouldn't know where it is, because it's going so fast. However, if we could cool an atom to absolute zero, we would know how fast it was going, zero, and where it was, which is not allowed. But like I said, you can't get to absolute zero for one reason. It's way too cold. And there's another reason where we can't get to absolute zero, called the unattainability principle. It says that the more heat you remove from a system, the harder it is to remove that next bit of heat, meaning that it will be infinitely difficult to get out the last bit of hot and reach ultimate cold. That's finished.